question 5 gives us the graph of y is equal to x squared. It then asks us to draw all these rectangles of width 1 over n that look like this. So this is going to be 2 over n, another 1 over n across. We'll get 3 over n, another 1 across. We get 4 over n, all the way up until we get the final triangle at 1. Alright? And we're asked to find out what's going to be the sum of these areas. If we added up all of these rectangles, what would we get? Well, what's the height? The height here, this is y equals to x squared. So this height here is the same as this point here, so it's going to be 1 over n squared. This height here is going to be 2 over n squared. This height here, we're going to get 3 over n squared. And up here, we will get 4 over n squared, right? All the way up until we get 1 squared. Okay, so if I called this rectangle in here my A1, this is A1, what is area 1? What is the area of A1? Well, the base is of course 1 over n. The height is 1 over n squared. Right? Now, let's look at this one next to it. This one's going to be called, funnily enough, A2. What's the area of A2? Well, the base is still 1 over n wide. Now, the height is 2 over n squared. If we look at A3, A3 is got a base here. So this is A3. And this base between here is going to be 1 over n. The height is now going to be 3 over n squared, because that's the height of this point, right? Then this one is my A4. A4 is going to be 1 over n times 4 over n squared. So if I can see the pattern, right, it's quite easy. The pattern is my rth rectangle has an area of base 1 over n times height r over n squared. Well, I want to know the area, the sum of all of these, of the areas of all of these rectangles, right? So I want to know what is my sum from r equals to 1 to n of AR, which is of course equal to the sum from r equals 1 to n of 1 over n r over n squared. So what do? Well, let's simplify it a little bit. This is the summation to n from r equals to 1 of r squared over n cubed. Well, n doesn't actually affect this summation at all, so I can pull it out. It's constant, that is, so I can pull it out. So 1 over n cubed is equal to the summation r equals 1 to n of r squared. Now at this stage, we realize that what we actually have is what they gave us. They told us what this is going to be. So we know that this is now going to be 1 over n cubed times n over 6, n plus 1, 2n plus 1. And then if we simplify it, this is now going to be 1 over 6n squared, n plus 1, 2n plus 1. And that's what we were asked to show for this part. What about the next part? Oh, sorry, give me a moment. Let me just get rid of these. Didn't quite do it all. Hold on. There we go. So for the next part, we have exactly the same graph drawn. So just give me a second here. X, Y. y, oh, where's my, there it is, y equals to x squared, and we still have rectangles here at width 1 over n apart. So this is again 1 over n, 2 over n, 3 over n. But this time, right, instead of taking, if we look up, here I took the higher end of my rectangle, right? So there are two ends, it's 0 and 1 minus 1 over n, so I took the 1 over n side. Here 1 over n and 2 over n, so I took the higher side. 2 over n and 3 over n took the higher side. This time, instead of taking the higher side, I'm going to be taking the lower side. So this first one is 0. Second one here has 1 over n squared. This one here, this one is my 2 over n squared. And then the next one up here would be my 3 over n squared. But I've run out of room. What's the final one going to be? The final one would be n take 1 over n squared. So let me look, we're then asked to find the sum of all of the areas of these smaller rectangles. So what's the area of the first one? If I called this rectangle in here B1, well, there isn't actually a rectangle in there, is there? So the area of B1 is 0, but we can rewrite this as having a base of 1 over n and a height of 0. B2, if we called this one in here B2, what do we get? Well, again, its base is 1 over n, and its height is 1 over n squared. What about B3? If B3 is this one in here, this is B3. Well, again, its width is going to be 1 over n. Its height is going to be 2 over n squared. So we can start to see the pattern again, and my B'rth term is going to have a width of 1 over n, a width of 1 over n and a height of r minus 1 over n squared. So again, we're asked to find out what is the sum of all of these smaller triangles, rectangles, sorry. And really what it is, it's the sum from r equals 1 to n of all of my BRs. So what's that? That's the sum, r equals 1 to n of 1 over n, r take 1 over n squared. Right. So I do something similar to what I did last time. So this is going to be the sum, r equals 1 to n, r take 1 squared over n cubed. N again can come out the front, so 1 over n cubed, summation n r equals 1, r take 1 squared. Now, we weren't given a formula for r take 1 squared, we're given a formula for r squared. Any way we can change this? Well, we have to play around a little bit. So, if I substituted in terms, what would this summation look like? Substitute in r equals to 1, I get 1 minus 1, which is 0 squared. So my first term is 0 squared, plus, so my second term, r equals to 2, I get 2 minus 1 squared, I'd get 1 squared, plus r equals to 3, I'd get 3 minus 1 squared, which is 2 squared, plus, all the way up until I put an n, where I'd get n minus 1 squared. So if we look at this, right, we could write this out as the sum from r equals 1 to n of r minus 1 squared. Or, we could also write this as the sum from k equals to 0 to n of n minus 1 rather, of k squared. So you can see how these two are going to be exactly the same. They both describe this exact summation. And because there's no need for me to add a 0th term, right? Like adding 0 does absolutely nothing. Instead of k equals to 0, I'm going to start with k equals to 1. Because it doesn't matter if I ignore this 0 term. So I'm just summing up all of these. Now I know how to, I know what this is thanks to the formula given in my notes in the book, right? this is equal to k minus 1 over 6, then it's k minus 1 plus 1, 2k minus 1 plus 1. What do I get? Sorry, not k. I don't know why I wrote k there. Should be... Oh, what was that? Shouldn't be k at any of those. It should be n minus 1 over 6, n minus 1 plus 1, 2n minus 1. There we go. So now what do we get? N minus 1 plus 1 is n, so one of these is going to cancel, so I'm left with 1 over 6n squared again, n minus 1 from here, and this is going to be 2n minus 2 plus 1, so 2n minus 1. And that's what I was asked to show. Now, with both of these graphs, right, as I get smaller and smaller rectangles, you can see that in every single one I've overestimated slightly, right? And all of these ones have overestimated the area slightly. Yep. As I get smaller and smaller rectangles, I'm going to get closer and closer. Like this bit that's overestimated is going to get smaller and smaller, and my rectangles will become closer and closer to the area under the curve. Similarly, this one, right? I've actually underestimated the areas. So as I use more and more rectangles, the area of the rectangles is going to get closer and closer to the area under the curve. Well, what does that mean? That means that if I'm looking at the limit, hold on, computer's taking a wee while here. There we go. If I want the limit as n tends to infinity of a, so as I use more and more boxes for in the form that I did for the first one, where it's slightly overestimating, well, we know that it's going to be the area under the curve. We know the same thing is true for the limit as n tends to infinity of b, right? And that both are going to be the area under the curve between 0 and 1 of x squared. So I can just integrate this. This is going to be a third x cubed between 0 and 1. So my final answer is a third. And I am done.